In this video, I'm going to show you how to recognize derivatives in limits. So here we want to compute the following limit. The limit as h approaches 0 of e to the power of 2 plus h minus e to the power of 2 all over h. Now just at a glance, does this limit look familiar at all? Well, it's just the limit of the difference quotient for the function f of x equals e to the x. So that means it's just a derivative of e to the x. To clarify, let's write this a bit more explicitly. Let's define the function f of x equals e to the x. Then using the definition of the derivative, we have that f prime of x is the limit as h approaches 0 of f of x plus h minus f of x over h. Now f is just the exponential function, so we can simplify this. This is the limit as h approaches 0 of e to the x plus h minus e to the x over h. And that really takes the form of our limit up here. The only difference is that here we've got 2 plus h instead of x plus h. But that's a simple fix because we just set x equal to 2. So we have f prime of 2 equals the limit as h approaches 0 of e to the 2 plus h minus e to the power of 2 all over h. And look at that, that's exactly what the limit is that we want to solve. That's exactly what our problem statement is. So let's go ahead and flip this equality around. This really just says that the limit as h approaches 0 of e to the 2 plus h minus e squared all over h, that is just equal to f prime of 2. So all that we have to do to get the result of this limit is we have to compute f prime of 2. And that's pretty simple because f is just the exponential function. If f of x equals e to the x, that means that f prime of x is just the derivative of e to the x, which is, well, just e to the x still. So f prime of 2 is just e squared. So there we have it. The limit as h approaches 0 of e to the 2 plus h minus e squared all over h is equal to f prime of 2, which we saw was e squared. So there we go. There is our final result. E squared is the value of the limit. Alright, so here's the next problem. We want to compute the following limit, the limit as x approaches pi over 2 of sine of x minus 1 all over x minus pi over 2. This limit should also look pretty familiar. It's very reminiscent of the other definition of the derivative, which goes like this. F prime at a point A is equal to the limit as x approaches A of f of x minus f of A all over x minus A. So let's go ahead and try to fit this derivative definition to the limit at hand. First of all, we see that x is approaching pi over 2, so that's an indication that a here would be pi over 2. So let's write that down. F prime of pi over 2 is equal to the limit as x approaches pi over 2 of f of x minus f of pi over 2 all over x minus pi over 2. So that matches up pretty well so far. The limit part matches up, the denominator matches up. It's just the numerator that we have to tailor a bit. We have to choose our function f so that f of x is sine x and f of pi over 2 is 1. And well, that's a pretty obvious choice. If we choose f of x equals sine of x, then this fits perfectly. F prime of pi over 2 is equal to the limit as x approaches pi over 2 of sine of x minus sine of pi over 2 all over x minus pi over 2. And let's go ahead and simplify this. So this is the limit as x approaches pi over 2 of sine of x minus sine of pi over 2. What is sine of pi over 2? Well, that's just 1. That's all over x minus pi over 2. And the left-hand side is still f prime of pi over 2. So this here matches up perfectly with our limit here. So this limit is really just a derivative. It's the derivative of the function f of x equals sine x. Alright, so if f of x equals sine x, then what's f prime of x? Well, just the derivative of sine, which is cosine. So f prime of x is cosine of x, and that means our limit here, the limit as x approaches pi over 2 of sine of x minus 1 over x minus pi over 2. We already know that's just the derivative, f prime of pi over 2, and we have our expression for f prime of x here. It's just cosine x. So this is just cosine of pi over 2, and cosine of pi over 2 is, well, just 0. So that's the value of our limit. It's just 0. Here's the next problem. The graph of the function y equals f of x is shown to the right. Which of the following statements is true? Statement 1, the limit as h approaches 0 of f of 2 plus h minus f of 2 all over h is equal to 3. Statement 2, the limit as h approaches 0 of f of 4 plus h minus f of 4 all over h equals 0. And statement 3, limit as h approaches 0 of f of 6 plus h minus f of 6 all over h equals negative 3. Alright, so at first glance this might seem like a lot of work. It looks like we have to calculate 3 limits, but actually it's a lot simpler than it seems. Each of these limits here is just a derivative of f of x. This first limit here is just the derivative of f of x at the point x equals 2. So we can convert this statement into a simpler statement. Statement 1 really just means that f prime of 2 equals negative 3. Let's go ahead and do that with all of the rest of the statements as well. So we'll get number 2, that f prime of 4 is equal to 0, and statement 3 will become f prime of 6 is equal to negative 3. But it still remains to determine whether or not these statements are true. So let's get to that now. Looking at the first statement, f prime of 2 equals negative 3. In the graph, f prime of 2 corresponds to the slope of the tangent line at x equals 2. And at x equals 2, the graph is a downward line. Why don't we check the slope of that line? Starting at, say, y-coordinate of 8 here, when we go over 1 unit in the x direction, we have to go down 1, 2, 3 units in the y direction. So the slope of that line, rise over run, is negative 3 over 1, or just negative 3. Let's write that down. So at that point, x equals negative 2, that slope is equal to negative 3. So that means this first statement is good, and thus so is the original form of it. Alright, next up, f prime of 4 equals 0. Is that true? Well, f prime of 4 is again just the slope of the tangent line at x equals 4. X equals 4 is here, and we're referring to this point over here. But hey, over there the graph has a sharp edge, so the derivative doesn't exist. So we can label this by saying that f prime of 4 does not exist, and if it does not exist, then it can't be equal to 0. So statement 2 is not correct. That means the original statement 2 is not correct either. And how about statement 3? F prime of 6 is equal to negative 3. Well, again, just the slope of the tangent line of the graph at the point x equals 6. That's right over here. So we're talking about at this point here, well, the graph is just a straight line. It's going upwards. Can that have a slope of negative 3? Well, at this point, we have that the slope is definitely greater than 0. So that means f prime of 6 has to be greater than 0, which means it can't be negative. If f prime of 6 were negative, then this section of the line would have to be going downwards. But it's not, it's going upwards. That means this statement is not true. That means the original statement is not true either. So which of the following statements are true? Well, 1 was the only one. So 1 is our final answer, just statement 1. So now we know how to apply derivatives to solve limits that take the form of a derivative. In the future, we'll continue learning how to differentiate more functions, such as composite, implicit, and inverse functions.